Hello everyone and welcome to this explainer. I am super excited you're here. We are tackling Chapter 6 today, three-dimensional geometrical shapes. Now, I know math revision can sometimes feel like you're just staring at a wall of disconnected formulas, trying to cram random letters and numbers into your brain, but hey, not today. Today, we're going to completely unfold the mystery behind these shapes. We are going to get into the exact why behind every single formula instead of just blindly memorizing them. By the time we're done here, these concepts won't just be rules on a page, they're going to be logical, fascinating tools that you completely understand. All right, let's dive right in. Okay, so here's our roadmap for this session. First, intro to solid geometry. 2, unfolding shapes with nets. 3, calculating surface area. 4, the secrets of volume. 5, solving combined shapes. And finally, 6, summary and exam tips.
Right, let's kick things off with Section 1, Intro to Solid Geometry. You know what's really cool is the origin of the word itself. Geometry isn't just some random math jargon. It actually comes from two Greek words, geo, meaning earth, and metria, meaning measurement. So, at its very core, geometry literally means measuring the earth. It grounds everything we study in the physical, real world around us. It's the study of sizes, shapes, positions, angles, and dimensions of actual things. And for this explainer, we're zeroing in on solid geometry. That means no more flat drawings. We're talking about three-dimensional objects that pop right out at you. You know, cubes, prisms, cylinders, and spheres.
Moving right along to Section 2, Unfolding Shapes with Nets.
So a crucial starting point here is understanding what a net actually is. In math, a net is what you get when you open and lay out every single surface of a 3D object so it becomes totally 2D. Just imagine taking a cardboard box, cutting along the edges, and flattening it right out on the floor. You're literally unfolding a 3D object until it's completely flat. Now you might be wondering, why on earth do we do this? Well, because seeing all those flat surfaces laid out side by side is the absolute secret to figuring out our first major calculation.
Which brings us to Section 3, Calculating Surface Area. Okay, here is the golden rule you really need to remember. Surface area is simply adding up all the surface areas of the 2D net together. That is literally it. If you've got a cube, you just find the area of one square and multiply it by 6, because, well, a cube's net is just 6 identical squares. Or if it's a prism, you find the area of that rectangular base, find the areas of the triangles on the ends, and just add them all up. Calculating surface area is exactly like figuring out how much wrapping paper you need to perfectly cover the outside of a box, with 0 overlaps and 0 gaps. You're just measuring each flat piece of that wrapping paper and adding them together.
But hold on a second. Adding up flat squares and triangles, that's easy enough. What happens when the shape doesn't have flat, straight lines? Like, how do we find the surface area of a curved shape, like a cone? Think about that for a second. You can't just unfold a curved surface into a neat, simple square, right? Or can you?
This right here brilliantly illustrates the absolute magic of geometry. Let's walk through this derivation. Imagine you take the curved side of a cone and you cut it into 88 equal tiny pie slices. We call them sectors. Now, if you arrange those 88 sectors together, alternating them pointing up and down, they actually form a rectangle. It's wild. The length of this new rectangle ends up being exactly half of the circular base's circumference, which is pi times radius. And the width is the slant height of the cone, which we call s. So the area of that newly formed rectangle is simply length times width, pi times r times s. To get the total surface area of the cone, you just add that curved part to the flat circular base at the bottom, giving you pi r squared plus pi r s. See? You don't have to memorize a random formula. You just have to realize that a curved cone can literally be sliced up and transformed into a simple, flat rectangle.
So, now that we've totally mastered the outside of our shapes, we need to compare it to the inside. Surface area is all about adding up those 2D nets to measure the outside wrapping. But volume? Volume is a whole different ballgame. Volume measures the actual amount of space an object occupies inside. If surface area is the wrapping paper on the outside of a birthday present, volume is the actual gift taking up space on the inside.
All right, Section 4, The Secrets of Volume.
The base rule for calculating volume is beautifully simple when you're dealing with uniform shapes. By uniform, I mean shapes that go straight up without getting wider or narrower. Think prisms and cylinders. The rule is just volume equals the area of the base multiplied by the height. You literally just find the area of the flat shape on the bottom and imagine stacking it up layer by layer until you reach the very top. But what if the shape doesn't go straight up? What if it tapers to a point, like a pyramid or a cone? Well, that requires a pretty special trick. Take a look at how we solve the volume for a tapered shape, like a pyramid. This is so cool. 6 identical pyramids can fit perfectly inside one single cube. Their pointy little tops all meet right in the exact dead center of the cube. And because they meet right in the middle, the height of one pyramid is exactly half the height of the whole cube. When you take the volume of the whole cube and divide it by those 6 pyramids, the math just simplifies perfectly. The 2 from the half height and the 6 from the 6 pyramids interact, and you are left with exactly 1/3. That's the secret right there. That is exactly why the volume formula for pyramids, and by extension cones, is always 1/3 times the base area times the height. It is not some random fraction somebody made up. It comes directly from the fact that 6 pyramids fit into a single cube.
Now, let's put this into practice. Section 5. Solving combined shapes.
Meet Salim. Salim is an ice cream entrepreneur, and he's got a real-world problem that is the ultimate test of our new volume skills. Salim sells his ice cream in a composite container. That just means it's made of 2 shapes joined together, specifically a cylinder with a cone right on top of it. He wants to know, if he aims to sell 10,000 of these combined containers in a single month, exactly how many liters of ice cream does he really need to manufacture?
Let's break this down. First, we need to calculate the inside space, the volume of each individual part. Using our formulas, the volume of his cylinder section comes out to 117.86 cubic centimeters. The volume of the cone section on top comes out to 26.19 cubic centimeters. To find the total volume of one single container, we just add those 2 numbers together, which gives us 144.05 cubic centimeters per container. But remember, Salim isn't making just one, he's making 10,000. So we multiply that single container volume by 10,000. That gives us a massive total of 1,440,500 cubic centimeters of ice cream needed for the month.
But wait, we aren't quite done yet. Salim needs to order his ingredients in liters, not cubic centimeters. Suppliers don't generally do cubic centimeters for large liquids. So the crucial point here is knowing how to convert. 1 liter is exactly equal to 1,000 cubic centimeters. So we take our massive number of 1,440,500 and just divide it by 1,000. The result? 1,440.5 liters. See that? By breaking a complex combined shape down into simple pieces and applying our volume rules, we just solved a very real-world business manufacturing problem.
All right, we made it to the end. Section 6, Summary and Exam Tips.
Huge congratulations on following the logic of that complex problem. Now let's rapidly review these key takeaways for the PT3 exam. Remember, geometry is grounded in reality. It literally means earth measurement. When you hear the word net, just think about unfolding a 3D box into a flat 2D piece of cardboard. To find the surface area, you're just finding the area of that flat 2D net, like wrapping paper. For volume, or the inside filling, uniform shapes are always just base area multiplied by height. But if it tapers to a point like a cone or a pyramid, remember the 6 pyramids inside the cube rule, you absolutely must multiply by 1/3. And finally, for those tricky word problems, always remember that 1,000 cubic centimeters make up exactly 1 liter. Because you now actually know the logic and the why behind all these formulas, you won't have to stress about rote memorization on exam day. You can just logically build the answers yourself.
Before we go, I want to leave you with one final, kind of provocative thought. We learned today that if you take the curved 3-dimensional surface of a cone, you can creatively cut it into 88 pieces and arrange them perfectly into a flat 2D rectangle to figure out its area. So think about this for a second. What 2D shape do you think a perfectly round 3D sphere unfolds into? Does it form a circle, maybe a weird series of triangles, or is the geometry of a sphere something else entirely? I really hope that mystery leaves you completely fascinated and eager to explore mathematics even further. Thanks so much for joining me in this explainer, and keep questioning the why behind the numbers. Catch you next time.